Hello students. So in the previous class we started with this higher order linear ordinary differential equation with variable coefficients, right? So we already know how to handle with constant coefficients. That means if you have like constants as the coefficient of the derivatives that are involved in the differential equation, then we know if it is a homogeneous type, then you can write down the general solution by solving the auxiliary equation. If not, then we have a non-homogeneous type, and then that can be tackled using complementary function and particular integral. Now likewise, we can generalize the idea of constant coefficients to variable coefficients. That means you will have functions of x as the coefficients in the derivative of the differential equation. Then in the previous class we saw that you can substitute x equals to e to the power z, and you can have something like so we can have so this is basically higher order ordinary differential equation with variable coefficients. So we can substitute x equals to e to the power z, and we can have dy dz equals to, basically we'll have dy dx into dx dz, and this will be dy dx into dx dz will be simply e to the power z. So that is x into dy dx. So in short, we can say that this d dash of y is equals to x d of y, or some people also prefer to write it d dash equals to x into d, where this capital D is nothing but d dx, and d dash is basically d dz, and so on. So similarly we can find out what is our x square into, we will see in several examples that instead of just x square, here you will have some other function like 1 plus x whole square and things like that. And how do we take care of those derivative terms, what kind of substitution? So it may be possible that we may not substitute x equals to e to the power z, but we have to substitute whatever is in here equals to e to the power z, and then we'll adjust the derivative term accordingly, right? And depending on the expressions of these, you will substitute them back into your given ordinary differential equation. And now it is no longer with respect to x, you'll have independent variable as z and a dependent variable as y. Accordingly, your right hand side, which was capital X, that was function of x, now it will be a function of z, right? And then we'll have an ordinary differential equation with a constant coefficient, of course non-homogeneous type, and then we'll solve the left hand side by this complementary function. So we'll determine the complementary function by taking the left hand side equals to 0, and we'll determine particular integral. Then we'll write down the solution in z, and then we'll again go back to x, right? So these are the several intermediate steps that we'll follow, and whilst solving the examples, I'll show you what I actually mean by them. Right. So let us start with the very first example. So that was just a recall of the previous lecture that we did, right? So to start with, let us consider this example. So we have, just to start with a simple one, okay, solve x cube d3y by dx cube minus x square d square y by dx square, and then plus 2x dy dx, 2x dy dx, then minus of 2y is equals to x cube plus 3x, right? So this we have to solve. So solution. So let us put x equals to e to the power z, so that we have, we'll have z equals to log x, of course to the base e, and accordingly we will have d dash equals to xd, and we'll have d dash equals to xd, then d double dash equals to x square. So here we'll have we have to simplify then. So this we have to calculate again, that means we have to do d square y by dx square here, then that will be, so I think we can calculate. So if I differentiate with respect to z again, so this will be d square y by dz square, then I will have x into d square y by dx square into dx dz plus this will be dy dx into dx dz. So I will get x into d square y by dx square, dx dz will be e to the power z plus dy dx into e to the power z. So this will become x square d square y by dx square minus x dy dx, but x dy dx is again dx dy dx is d dash y. So this will be x square d square y by dx square minus of d dash y. So you bring that on the left hand side. So I am sorry for the space crunch here. So it will be d dash square of y plus d dash no, this is plus, no, x into dy, this is plus, this is plus. So here it will be minus equals to x square d square y by dx square. So from here I will take d dash out, and this will be d dash minus 1 into y equals to x square d square y. So likewise we can be able to determine d3 also. So x cube into d3y, and we will see that it will be d dash into d dash minus 1 into d dash minus 2 and so on. So that means this d dash equals to xd, then we have d double dash minus of d dash equals to x square d square, then we will have d dash minus 1 and d dash minus 2 equals to x cube d cube and so on. So likewise we can determine the other higher order derivative terms. So now we will put everything back into the equation number 1. So this will reduce to it will be a slightly a bigger calculation, but I think we can still be able to d dash minus 2 minus of x square. So this is d dash minus 1 plus 2 plus 2 d dash minus of 2 of y is equals to e to the power 3z plus 3 e to the power z, right. So if I simplify it further, so then this will yield something like this. So this will give d dash minus 1 whole square into d dash minus 2 into y is equals to e to the power 3z plus 3 e to the power z, right. So here the auxiliary equation, so this is equation number 2. So now we will treat this as ordinary differential equation with constant coefficient, non-homogeneous right hand side. So this will eventually lead to doing that complementary function and particular integral. So here the auxiliary equation 2 is we will have m minus 1 whole square into m minus 2 equals to 0. So from here I will get the roots as 1, 1 and 2. So the complementary function to equation 2 is we can write ycz is equals to c1 plus c2z into e to the power z plus c3 e to the power 2z. Let us call this as equation number 3. Now we are yet to determine the particular integral. So the required particular integral, the required pi is given by y p z is equals to 1 by d dash minus 1 whole square and then d dash minus of 2 e to the power 3z plus 3 e to the power z. So, now we will distribute on each term. So, d dash minus 1 whole square, d dash minus 2 e to the power 3z plus 1 by d dash minus 1 whole square, d dash minus of 2 into 3 e to the power z. So, 3 is immaterial, we will just bring it on the left hand side. Achha. So, the first one is very simple to see, because when you substitute d dash equals to 3, then it is not becoming undefined. So, the first term is very easy to determine. So, it will be e to the power 3z and then I will have 3 minus 1 and then 3 minus 2. Whereas, for the second one I can substitute d dash equals to 1 in this d dash minus 2, but not in d dash minus 1 whole square, because that one will become undefined. So, this is okay, and then this one will be 3 into 1 by 1 minus 2 into 1 by d dash minus 1 whole square into e to the power z. So, from here I will get 4, 1 by 4 e to the power 3z and then minus of 3 e to the power z 1 by d dash minus 1 whole square. So, now when we know if fd is becoming 0 at d equals to a, then instead of fd we put d plus a, right. So, this will become 1 by 4 e to the power 3z minus of 3, then 1 by will have d dash plus 1 minus of 1 whole square e to the power z. E to the power z will come this side, right. E to the power z will come this side, and this will be simply 1. This will be simply 1. So, so basically this will give this will give 1 by 4 e to the power 3z minus 3 e to the power z, then 1 by d dash square of 1, right. So, here we are treating that x into e to the power v into e to the power ax form. So, e to the power ax came this side and we substituted d as d plus a or d dash as d dash plus a. So, here we are integrating 1 twice. So, if you integrate 1, so it will become z. If you integrate it twice, then it will be z square by 2. So, this will become 1 by 4 e to the power 3z minus 3 e to the power z into z square by 2. So, here we have 1 by 4 e to the power 3z minus of 3 by 2 z square e to the power z, right. And therefore, the required solution to equation 1, that means the original equation. So, first of all we write y of x equals to y complementary function with respect to x and particular integral with respect to x. So, complementary function was c1 plus c2z plus c3 e to the power 2z, and this one was 1 by 4 e to the power 3z minus of 3 by 2 z square e to the power z, where z equals to log of x. So, let us keep replacing. So, this will become c1 plus c2 log of x plus c3 e to the power 2 log of x plus 1 by 4 e to the power 3 log of x minus 3 by 2 log of x whole square into e to the power log of x. Achha. So, this will give c1 plus c2 log of x, then this will become c3 x square plus 1 by 4 x cube minus 3 by 2, this will be x log of x whole square, and this is the required general solution that we are looking for the equation number 1 that is given to us. Slightly lengthy, but I think the algorithm, the process is very much clear, that you reduce the equation which was in terms of x to an equation which is in terms of z, that means the independent variable has now been changed from x to z, then you solve that equation, I mean calculating the complementary function and then by calculating the particular integral, and from there we write down the solution in terms of z and then substitute it back to the variable x, and that is pretty much the flow chart you can say we are following. Right, we'll solve maybe couple of more examples just to make you understand further. So let us go to next page probably. All right, so the next problem that we want to consider is of this type. So example 2, right. Let us say we have something of this type 1 plus 2x, as I was saying that it can be different than simply x square, right. So 1 plus 2x d square y by dx square minus of 6 into 1 plus 2x dy dx plus 16y is equals to 8 1 plus 2x whole square, right. Solution. There is one particular thing that we can notice about this equation. It has a singularity at x equals to minus half, right. Here the range and domain and all those things are not given, but if you substitute x equals to minus half, then basically you will end up getting y equals to 0, right. So that is the only solution. Then it will simply become an algebraic equation, right. And why we are saying singularity, because if you divide both sides by 1 plus 2x whole square, then it will become 1 here, 6 by 1 plus 2x, and here it will be 16 by 1 plus 2x, and at x equals to minus half, the second and third coefficients are becoming undefined, and that is why or infinity, and that is why this equation has a singularity at x equals to minus half. But we are not looking into that part because that will come later. So when we learn about series solution, there we will talk about the singularity and all those things. So for the time being, this is the given equation, right. Now here the idea is same. Instead of substituting x equals to e to the power z, we will substitute this entire thing, right. So let us put 1 plus 2x equals to e to the power z. So then we will have z equals to log to the base e 1 plus 2x. Alright, so I will just calculate dy dx, rest of them I expect you to calculate. So dy dz into dz dx. So here I have dy dz into dz dx. So dz dx will be dz dx will be 1 by 1 plus 2x into 2. So that means 2 dy dz equals to, that means 2 d dash y is equals to 1 plus 2x into dy dx, or you can write in short 1 plus 2x into d of y, right. So at least we know this can be replaced by this. Similarly, we can calculate the second order and put everything back into the equation number 1. So similarly 1 plus this, you have to calculate in your examination, d square x by d. Similarly this can also be simplified, Alright, so then what will happen here is if we substitute everything back there, then it will then equation 1 reduces to 4 into d dash minus 1 minus of 12 d dash plus 16 y equals to 8 e to the power 2z, because we have 1 plus 2x whole square. So 8 e to the power 2z. So this can be further simplified to 4d dash minus of 8d, so minus of 16d dash 16 d dash d dash square 16 d dash plus 16 y, right, equals to 8 to the power 2z. So, that means I can cancel out 4, and therefore, this will become d dash square minus of 4 d dash plus 4 equals to 2 e to the power 2z. Let us call it as equation number 2. So, therefore, the auxiliary equation, the auxiliary equation to equation 2 is given by m square minus of 4m plus 4 equals to 0. So, from here we will get m equals to 2 and 2, right. So, therefore, the complementary function for equation number 2 is ycz equals to c1 plus c2z into e to the power 2z. So, we are able to determine the complementary function. Now, let us proceed to determine particular integral. Okay. So, now the particular integral can be given by yp z is equals to 1 by what do we have? We have d dash minus of 2 whole square 8 e to the power 2z. But again this creates a problem if you substitute d dash equals to 2. So, here 8 will come out anyways, and then this falls into the category of v into e to the power ax. So, you substitute d is equals to d dash plus a, you bring e to the power ax out of the integral, this 1 by d dash 1 by fd, and then you charge this 1 by fd to that remaining function, which is basically 1. So, here what we will do, we will write 8 e to the power 2z 1 by d dash plus 2 minus of 2 of 1. So, this will become 8 e to the power 2z 1 by d dash square of 1. So, that means 1 by d dash square means we are doing integral twice. So, this will become z square by 2. So, 8 e to the power 2z into z square by 2. So, this is 4z square e to the power 2z, or we can write 2z e to the power z whole square, right. So, this can also be possible. Therefore, the required solution to equation 1 is given by yx equals to ycx plus ypx. So, ycx is c1 plus c2z into e to the power 2z, right, e to the power 2z, and particular integral is oh, it is not 8 actually, wait a minute, is it 2? I think that's 2, sorry, it is 2, not 8. So, this is 2. So, this is 2, and therefore, this 2 and 2 will get cancelled. So, there will not be any 4, it will be just z e to the power z whole square. So, then this will become c1 plus c2, z is 1 plus 2x log of 1 plus 2x, and then this will be e to the power 2 log of 1 plus 2x plus log of 1 plus 2x e to the power log of 1 plus 2x and whole square. So, I believe it can be further simplified. So, 1 plus 2x whole square c1 plus c2 log of 1 plus 2x plus this will become 1 plus 2x log of 1 plus 2x. I hope this calculation is correct. Rest of the verification that you can do. So, if there are any error with plus, minus, or taking the coefficients like or constant, so that you can rectify. But the idea is you calculate the complementary function, you calculate the particular integral, and then you write the solution in terms of independent variable z, and then you do the reverse substitution. You go back from z to x, right, and then we write down the required solution, which is basically the general solution of your given second order ordinary differential equation with variable coefficients, right. So, as I was saying, instead of let us go back to the problem, instead of having only x square, we may have this term here, and this creates an interesting situation that what can be the substitution, whether you take x square or whether you take the whole 1 plus 2x square into d square y by dx square, right. There can be further complication, I mean not complication, but there can be further generalization, which is really not difficult to handle. So, example 3, I am not going to solve it, I will just write it for your own exercise. So, x to the power 4 d to the power 4 plus 6 x cube d cube plus 9 x square d square plus 3 x d plus 1 of y equals to 1 plus log x whole square, right. So, 1 plus log x whole square. So, here we can see we have x to the power 4 d to the power 4. So, it is not difficult to handle, you just have to determine the expressions for x dy dx, s square d square y by dx square, x cube d square d3 y by dx cube, and x4 d4 y by dx4. Substitute all those things in terms of d dash, then you do some simplification, some cancellations may happen, and then ultimately our auxiliary equation will reduce to something like this: d dash square plus 1 whole square of z equals to 1 plus z whole square. Now, how did we obtain this? That you have to do some simplification, putting that x equals to e to the power z, and see whether we can get this expression or not. It may be possible that this might be wrong, but you have to just do the calculation and see whether it is right or whether it is incorrect, right. We can increase the power if you want. Instead of x to the power 4 and d to the power 4, we can have something like let us say x plus a, another exercise for x plus a whole to the power 3 d3y by dx3 plus 4 x plus a dy dx plus 6y equals to x, right. So, something like this, and this should be negative sign. So, something like this, and then we substitute the again x plus a equals to e to the power z. You calculate all the derivative, put it back, and then simplify. Some cancellations will happen. Resulting equation is a differential equation with respect to independent variable z. So, then we will determine the corresponding ODE. From the ODE we write down the complementary function, and then we write down the particular integral. When we add them, we get the required general solution, and then it should be reversed back to the variable x. So, that is the working principle for ordinary differential equation of higher order with variable coefficient. So, we have seen for constant coefficient, and now we are looking at the examples for variable coefficient.